reminded me of something. The definition of standard state is the pure material in its most stable state, solid, liquid, or gas, as whatever it is at a pressure of 1 bar and the reference temperature. Standard state of helium is gas. Standard state of iron is actually solid. In the particular crystal structure of iron, it's stable at a pressure of 1 bar and 298 Kelvin, and I don't know what that crystal structure is. I have just enough time to talk about formation. Formation refers to forming a chemical substance I just realized maybe I shouldn't do that yet. Maybe we'll do formation on Tuesday. I need to do something else first. I'm going to come back over here to do that. One interesting way of thinking about Newton's law is to do it graphically, to make a scale of enthalpies. And we know from wherever hydrogen and oxygen are that forming water, we go down 285 kilojoules per mole to find water in the gas phase. That's lower in enthalpy. And I'm making that pretty small because if you react boron and oxygen, you've already got oxygen there, and make boron trioxide, diboron trioxide, it's way down there. Minus 2,368, and I guess I'll make the scale accurate. There's water. This is minus, well, it's that number, minus 2368. And we can get this one too, burning. Let's see, burning, we've got, well, you have it up there. If you burn diborane, we make this same product and water. So we sort of have to take an average of this. And when we burn it, we make one of those in 3 waters. So we sort of are 1/3 here and 3/3 there. So that's sort of the weighted average of those two. And when you burn that, the diborane was 1940 watt above it. That's kind of complicated because this comes down to form these two different things, but you have to take the weighted average of those. You have one of those and 3 of those. The weighted average is maybe here. If we keep doing that with lots of different things, we can put lots of different levels on there. But really what we're doing is just talking about the differences between these levels. It would be nice if we had a 0 on that scale, but we don't. What we can measure in the laboratory by calorimetry is only the difference between here and here, or there and there, or wherever they are for our given reaction. We can measure the difference in enthalpies. We have no idea if there is even a 0 on that scale, and if so, where it would be. That's not a satisfying place to be. Interformation reactions. Formation reaction is by definition forming a chemical substance in its standard state from the elements contained within that substance in their standard state. For example, this reaction number 2 up here is a formation reaction, forming diboron trioxide from the element oxygen and the element boron. Consider this formation reaction. Let's form sodium. And the standard state of sodium is solid. And what are we going to form sodium from? By definition, what do we form it from?
Their standard states.
The elements. What elements are involved here? Sodium in its standard state. What's the enthalpy change for that process? It would be 0.
Okay, thank God.
Because nothing has happened.
I don't understand anything.
I have sodium, and I make sodium from it. Is there a reaction taking place there?
No.
No. There's no reaction, so there's no enthalpy of reaction. Why bother? Why bother with all of this stuff?
Now suppose that we're making sodium chloride.
This is a formation of an element from the element. And for that process, that is, since I've taught it's a formation, it's dealing with, where are they here? Standard states. It is a formation reaction, the enthalpy and standard state of which equals 0. There's 0 for our enthalpy scale. Through the definition of a formation reaction, we can now say that the enthalpy of formation of the elements in their standard state is 0. And interestingly, I didn't tell you why at the time, but I put all of those elements at the same level, because that is 0 on our scale. We now have a 0 on the enthalpy scale that we can measure everything else with respect to. And this may seem like a bunch of busy work, but it's crucially important. It's crucially important because that definition gives us that 0 on the scale. Without it, we wouldn't know where 0 was, and all we could talk about is the difference between levels, and pretty quickly we're going to get so many levels there, we're not going to be able to tell what's what when you start putting 10 or 12 or 15 reactions on one table. What does this allow us to do then? Well, if we measure